So our first topic today, I'm just going to scroll back to the course outline and start our conversation with refreshing what we already know about the interfaces. So interfaces, actually, sorry, I clicked on inheritance. The interfaces here. Interfaces are directly related to inheritance and are very helpful in organizing a framework of classes that are related. So anytime we have the presence of an interface or the presence of inheritance between classes, we definitely can say that the classes are related. In many cases, when you work with someone else's project and it already has a lot of classes, you're very likely to begin your understanding of that project by analyzing what interfaces exist and what classes people have created. So, quick overview. Perhaps we can draw a little simple demonstration of using the interfaces. Let's see. I'll just use paintbrush here. So here, if I have a set of classes, and these classes are, for example, I want to store models of 3D shapes, right? So I can say I have a model class, and then it has a set of properties and certain methods, and I would like to be able to say this is a road racing game. So I can have a car, a racing car, or simply car as a class. I can have the terrain, right? This is another part of my model. I can have a sky, so that I can draw the sky. I can also have stands, right, like spectator stands, bleachers. I can have trash cans, right, around the terrain or alongside with the road, and many other things, right? So these are all sort of like classes that I'd like to have. And I think it's reasonable to expect that these classes are drawable classes, something that I can draw in my game if I'm planning to design a game. So I can create these classes and use them in a game. Okay, so this is the fact that I can draw them is pretty much what makes them related. In fact, I will switch from plural trash cans to just a trash can, from stands to stand, right? So if I have this a relationship, you know, from UML diagrams, what we do is that we use this type of relationship and we say all of these are drawable models, and we can use UML generalization notation to show that these classes will be related. How is this helpful? If I can create like an array list collection, we'll say array list. If I say array list of these models, okay, I can have an array list of models, and I can name those. In fact, this is the type of the class that I'd like to use to store my models. What it allows me to do is that then I can switch to this type of collection, and this collection at runtime can be populated with the references to these specific objects that I want, right? So the objects like car objects will be instantiated. There may be a few of these cars in memory when I start this racing game, right? There could be also one terrain object over here. They're all different classes, and there could be a sky object, which is typically a projection of like pictures, left, right, front, back, up, down to a box, and you get this box view from inside, right? And you can have stands or bleachers, you can have trash cans, and many of these. So to say, having this array list of models helps me to organize them in memory as uniform collection, right? A collection of likewise objects, so that these references basically point to these objects in memory, and I'm organizing my game this way. So why is this helpful? Because now, if the model from which all of these classes derive have a method named draw, right? Draw, for example, right? Draw. Then I can iterate through this collection, like visit every object in this collection in a loop, and basically tell each object reference that I want to draw you. But you know how when I draw these boxes representing actual objects in memory, I typically do not, or I should say that I do not include any methods in them. Instead, methods are placed outside of any object, and an executable code representing these methods is located elsewhere in memory, right? So everything that I draw on this right-hand side of our diagram is pretty much like my visualization of what happens in computer memory. But we say that with each class that we create, what Java does, it builds a little table of all methods that belong to each class, right? And when we create objects of specific type, say this is a car, this is also a car, this is say a skybox, this is a trash can, and so forth. Then, if these are two car objects, they have a hidden pointer, right, to the table in memory, which tells the compiler where specific methods for this particular type of object are located. And so this way, if I iterate here, what happens is this: I find an object of type model, because I stored model references in this array list, because this is array list of models. But at runtime, this polymorphic behavior, what it does is that if I say draw, right, if I use this specific object to say I want to draw this on my screen, then what it does, it finds this hidden reference to the table of methods, and it would find the draw method which is specific to the car, and say this is the place where the code will execute. If this reference is pointing to a trash can, so trash can implementation of draw is very different compared to the car, and so it has its own hidden reference to the table that represents method that belong to the trash can, and it will say that your method of execution is someplace else, and this will execute, right? So this is the type of indirection and layers that really exist to support polymorphic behavior. And today we're simply going to explore an ultimate version of this behavior, where we can say that our classes will not simply derive from a specific abstract class, perhaps such as model, but rather they will be using an interface, a common interface, and they will be implementing, say, iDrawable interface, and iDrawable interface will include the draw method, and dynamic polymorphism is going to work exactly the same way. may have the convenience of populating a collection of items and using the interface type to store in this collection. But at runtime, when you use methods of this interface, because each class implements the interface, the object will contain a pointer to the table which represents the methods, the addresses of methods in memory which need to be invoked, and each specific object type will delegate the draw call to a specific executable code which was originally made part of this class or that class. So this is the high-level view of how interfaces can be effectively used, at runtime. So this time, let's switch to the presentation, and we'll do like a few slides, and then maybe we'll start practicing writing some code and experimenting in the code window with those ideas.